Hey guys, today we're going to be doing this Gibbs free energy practice. The problem says for ammonia and H3, the enthalpy, delta H, of fusion is from a solid to a liquid, it's a process of melting, is 5.65 kilojoules per mole, and the entropy of fusion, same thing, same process, is 28.9 kilojoules per mole. The first part A asks us to if it will melt spontaneously at 200 degrees Kelvin. So what it's asking in essence, it's asking for if something is spontaneous, right? So we need to calculate for delta G. And the rule is that if delta G is a negative number, it is spontaneous. If delta G is a positive number, it is not spontaneous. So now we have the formula for delta G, which states that delta G is equal to delta H, enthalpy, minus the temperature times our entropy. Now we're solving for delta G. So delta G equals, they give us our enthalpy of fusion, which is this, and it's 5.65. Oh, well, this is in kilojoules. I'm gonna, instead of putting it in kilojoules, we're gonna multiply by 1,000. So instead of 5.65, it's 5,650 minus the temperature, which is given at 200 degrees Kelvin, and it has to be in Kelvin, times the 28.9, which we don't change because it's already in joules, and that gives us a value of negative 130 joules per mole. Since our delta G is negative, this reaction is spontaneous and it will melt spontaneously. And the reason that it has to be negative is because in sum, once you go through a breakdown of the equation for how you get delta G, and you divide out, you find that in sum, the delta S, the entropy of the universe, can be summed to this. And if our delta G is negative, that means that the delta S of the universe will be positive. And that's what you want. When chaos is going up, you want your delta S to be positive. If it's not, then more order is happening and there's less chaos. Okay, so the next part of this question actually asks what is the approximate melting point. And what they mean by at melting point, this is at equilibrium, which means that you're at, like, let's say, like, the 0 degrees Celsius, which means that your delta G actually has to be set to 0 here. This is the concept here. The concept is that this is at 0. Your delta G is at 0. What you're solving for in sum here is your temperature, right? And if you couldn't see that, you would also just figure it out because you don't have a temperature and they're giving you this and they're giving you this. Okay, so now we have the formula delta G equals delta H minus temperature times the entropy, right? And if I'm setting this to 0, that means that 0 is equal to the enthalpy minus the temperature times the change in enthalpy. And then I can rewrite that to say that the temperature times the change in enthalpy is equal, the change in entropy is equal to the change in enthalpy. It's a play on words here, guys. Okay, so the temperature is what I'm looking for. So I can say that my temperature is equal to my enthalpy divided by the entropy, right? Which leads me to, I'm going to convert this to joules as well. They have to be in the same unit. Also 5650 out of 28.9. And let me just calculate that. 5650 divided by 28.9. That gives me 195.5. I'm going to round it, so 196 Kelvin. So the approximate melting point of ammonia would be 196 degrees Kelvin.